Try to imagine a world without tools, without built shelters, without control over fire. A world where simple objects like ropes, containers, or blades simply didn't exist. It seems unlikely today, but that was exactly the starting point of our species. During the Stone Age, mastering solid materials wasn't just a matter of survival. Each advance, no matter how small, paved the way for something greater. Over the centuries, we discovered that it wasn't just what was hard or resistant that mattered. Liquids and gases also began to gain space in our evolution. Water, for example, stopped being just a source of life and became a controllable element. And today, gases power everything from jet engines to space rockets. Even if we don't realize it, matter is shaping the world around us all the time. In this video, we're going to explore the three most familiar physical states: solid, liquid, and gas. These aren't the only ones. There are states like plasma and Bose-Einstein condensate, but they belong to another level of study. Today, we're going to focus on the states that inhabit our daily lives, and looking at them carefully can reveal much more than we imagine. Why are some things so firm, others so fluid, and others still as unpredictable as air? Maybe you think you already understand everything about this topic, but knowing the states of matter is more than reviewing school concepts. It's opening your eyes to the invisible structure that sustains the world, a living structure in constant motion, shaped by energy, temperature, and molecular interaction. Ready to begin this journey? When we talk about solid matter, we're talking about what seems unchangeable to our eyes. A stone, a blade, or even a block of metal. They all share something in common: defined shape and volume. This happens because their molecules are incredibly close to each other, organized in fixed structures. This organization gives rigidity and stability. It's no wonder that ancient constructions resist time for millennia. The secret lies in this microscopic order that keeps everything in place. Within this solid world, there's a fascinating group: crystals. They're not just beautiful, they're incredibly well organized at the atomic level. Snowflakes, mineral salts, and even quartz follow a structure called a crystal lattice. It was only in 1912, with experiments using X-rays, that we managed to prove this arrangement clearly. It's as if, for the first time, we saw the hidden symmetry behind what seemed like just a block. Since then, crystals stopped being merely aesthetic and gained fundamental roles in science and technology. Quartz, for example, is more than a pretty stone in jewelry. It vibrates so precisely that it became essential in watches, microcontrollers, and communication systems. In electronics, this property is used to create stable frequencies, fundamental for the functioning of countless devices. It's no exaggeration to say that today, much of modern technology relies on a little piece of crystal, and all of this is born from the perfect organization of its particles in solid state. Beyond the beauty and precision of crystals, the solid state also sustains tools of our daily life: ropes that don't give way, springs that store energy, scales that maintain balance. All of this depends on the rigidity and stability of this state. This resistance comes precisely from the firm structure of molecules, which strongly oppose any attempt at deformation. It's this resistance that made solid matter the foundation for weapons, measuring instruments, and construction since the dawn of civilization. If solids impress with their rigidity, liquids fascinate with their fluidity. They have defined volume, that is, they always occupy the same amount of space. But unlike solids, they don't maintain their shape. If you put water in a cup, it takes the shape of the cup. If you transfer it to a bowl, it changes contour. This ability to adapt comes from the fact that, although molecules are close together, they move with more freedom. There's order, but a more flexible order. This flexibility brings unique characteristics, like resistance to compression. Try squeezing a bottle full of water. It's difficult, isn't it? This happens because the molecules are already quite close, and there isn't much space to reduce. But the fluidity of liquid allows it to move easily from one place to another. In hydraulic systems, for example, this property is essential. The pressure applied at one point distributes efficiently, moving machines and mechanisms with precision. Another fascinating property of liquids is surface tension. It's what allows raindrops to form, a needle to float on water, and certain insects to walk on the surface without sinking. This invisible force between molecules creates a kind of elastic skin on the liquid surface. It seems like magic, but it's pure physics. It's this same phenomenon that allows you to drink with a straw or water to climb up through absorbent paper. Finally, we have viscosity, which is resistance to flow. A liquid like water has low viscosity. It flows easily. Honey or shampoo, on the other hand, are denser and flow slowly. This influences everything, from choosing motor oil to the behavior of toothpaste. By the way, have you ever noticed how it seems solid inside the tube, but flows as soon as we squeeze? It's a good example of how the liquid state can behave in complex and adaptable ways. And it's this complexity that connects the liquid state with modern technologies and everyday solutions. Of the three most common states of matter, gas is the hardest to visualize, but perhaps the most present. The air we breathe, steam coming from a kettle, or gases that power engines, all are examples of matter in expansive form. Unlike solids and liquids, gases have neither defined shape nor volume. They mold to the container and spread wherever there's space. This happens because their molecules are well separated and move with complete freedom. This molecular freedom results in very different behavior. In gases, interactions between particles are almost null. It's as if each molecule follows its own path, without caring about the others. That's why they're easily compressible. In oxygen cylinders, for example, a large amount of gas is stored under high pressure. When opening the valve, it expands immediately. This behavior is what makes gases so useful in engines, controlled explosions, and even refrigeration systems. If we observe planets and stars, we'll notice that gases dominate the visible universe. But these gases only stay together thanks to a natural trick: gravity. Without it, molecules would disperse into space. That's why planetary atmospheres are fragile. It only takes a loss of mass or gravitational field for gas to escape. In the sun, hydrogen and helium are gases under intense pressures. That's why they behave completely differently from what we see on Earth. And unlike liquids, gases don't form drops. There's no significant surface tension. You can't see a gas bubble floating in air like we see with water. But still, their applications are vast. We have weather balloons, car airbags, propellants and aerosols, and airplane turbines. Understanding the gaseous state is understanding free movement and expanding energy. It's comprehending the invisible mechanisms that fuel much of the technology that surrounds us. These properties we've just seen aren't just scientific curiosities. They built our civilization. Since ancient times, the solid state has been essential for humanity's advancement. It was with stones that we shaped the first tools. Later, with metals like bronze and iron, we created weapons, bridges, structures, and transportation systems. All of this was only possible thanks to the rigidity, resistance, and stability of solids. Every hammer, wheel, or building is a testament to the importance of this physical state. Without it, engineering and architecture simply wouldn't have existed. But it didn't take long for us to realize that, despite being invisible or unstable at first glance, liquids and gases were also powerful allies. Understanding liquid behavior allowed the emergence of hydraulic systems, agricultural irrigation, and even car brakes. Meanwhile, gases transformed the world by enabling combustion engines, rockets, turbines, and complex industrial processes. All of this comes from the ability to control expansion, compression, and stored energy in these states. Space exploration, for example, would be unthinkable without mastering all three states. Solids provide spacecraft structure, liquids are used as cryogenic fuels, and gases control pressure, propulsion, and life support systems. Airplanes also combine these properties: rigid wings, hydraulic fluids, and jet engines powered by high-speed gases. Every modern technology is, in some way, a direct result of deep understanding of matter physics. This integration of physical states is also seen in magnetic levitation trains, nuclear power plants, air conditioning systems, and electronic sensors. Even the functioning of a simple stove depends on these principles. When we understand solids, liquids, and gases, we gain power. The power to manipulate, adapt, and transform reality. And although many of these applications are present in our daily lives, we rarely stop to think that all of this begins with something so seemingly simple: the state of matter. Everything we've seen so far reveals something profound. Behind the matter that makes up the world, there's a delicate balance between organization, movement, and energy. Each state of matter is a unique manifestation of molecular interactions that occur on invisible scales. Understanding these behaviors is more than a theoretical exercise. It's an invitation to see reality with more clarity, more respect, and why not, more fascination. Understanding the physical states of matter also connects us with humanity's history. From the first chipped stone to space propulsion systems, everything went through this knowledge. Knowing how and why a material behaves in a certain way is what allowed us to build bridges, cure diseases, fly, explore space. And this is just the surface. Behind each application, there's a molecular dance that shapes how everything works. But this is just the beginning. If physical states already show so much, imagine what we can discover by exploring concepts like pressure, gas laws, or even buoyancy. These are topics that seem distant but are present in everyday situations, from diving in the sea to how an airplane works. Science isn't just in books, it's in the glass of water, in the wind that blows, in the flame of a candle. And the more we see this, the closer we are to reality. So here's the invitation. Keep exploring with us. In the next videos, we're going to dive even deeper into these phenomena. If you enjoyed this journey, subscribe to the channel and activate notifications so you don't miss the next content. And now tell me, which of these 3 states of matter surprised you most? And in what part of your daily life do you see hidden science, waiting to be understood?